everybody. Welcome back to Young Engineers of Today. And I'll be ready to continue with bridge building because that's what we're going to do today. Last class on Monday, I gave out the links, or the link rather, the singular link for the previous versions of the bridge design contest software, or bridge designer software, or whatever. Hopefully you guys followed that link and at least downloaded it. I am behind the curve on everything, so I downloaded it. I have not installed it yet. So just in case you're unsure as to how this goes, well, I can show you. At any rate, it's a fairly straightforward installer. If you get to this point, install for anyone using this computer or install just for me. Personal preference. Doesn't really matter. And then pick a spot for it. I choose to not create shortcuts because I don't really have a start menu anyway. And I don't want like a desktop icon because I have enough stuff on my desktop as it is. Anyway, last class we went over the forces, the loads, materials, and the shapes that I'll go into making a bridge, which was a lot of stuff. Yeah, I know, Liam. It's really not that bad once you get used to it. It's 8.1, by the way. But anyway, yeah. It's a lot of stuff to go over. So, I mean, I'll spend a few minutes just sort of quickly going over it again. But by and large, it's all fairly straightforward stuff as well. So, you don't really have to worry about, oh, I have to remember all of this stuff. We'll go over it again as we're creating these bridges using the Bridge Designer software. So you'll get a better idea for how all this stuff sort of works together in order to create a fully working bridge. But yeah, forces that they undergo: compression, squeezing, tension, pulling, shearing, twisting, and bending. And those can be caused by the weight of the bridge itself, the weight that the bridge is carrying, which could be, still loads or moving loads, static or dynamic. Temperature can play a factor into whether or not the bridge is experiencing stressing forces because materials expand and contract with temperature changes. Earthquakes can certainly create a load on the bridge, exert forces on it and stress it. Wind is definitely a big one. And then as far as what you can build bridges out of, you can build them out of wood, which is great and cheap, but you need to keep maintaining it and it can catch fire. Concrete, also good and cheap, because you're basically just building a bridge out of rocks or rock. But and it handles compression well, and it doesn't really catch fire, but it doesn't handle tension well, and temperature changes can really affect it. See potholes. Reinforced concrete can do compression and tension pretty well, so it can solve the tension issue that regular concrete has. It's still pretty cheap, and it is still fireproof and weatherproof. On the other hand, thermal loads, so temperature changes can affect it. Then you get into metals, so like cast iron, very easy to shape. It handles compression very well. It doesn't catch fire, but it's expensive, doesn't handle tension well, and there's no real lead up to it breaking. It'll just break. Steel, very strong, forms in any shape, very protected against the elements, but it's super expensive. Then finally, we went over the shapes of the bridges, rectangle being the least stable, arch being better, and triangle basically being the best as far as distributing stress is concerned and being able to handle larger loads. Finally, we went a little over the history. So Rome was really the big player for big complex bridges back in the day with the arch bridge. Not much happened after that until iron happened, and then we got suspension bridges, which are big deals because they allow you to cross much greater spans with less material and fewer supports because the supports at either end hold up the bridge. On the other hand, suspension bridges can sometimes be a problem because they're so flexible. The flexibility allows them to withstand more force, certainly, but sometimes that flexibility can be its downfall, such as Tacoma Narrow Suspension Bridge. But sometimes you need flexibility, like in earthquake-prone areas, hence the Golden Gate Bridge. So yeah, engineering oftentimes is all about finding the best solution for the situation that you're given. You're not necessarily going to build a suspension bridge over a 5-foot span out of steel because that's just kind of absurd. But, you know, by the same token, or on the other hand, I suppose, you're not going to build a 1,000-foot span bridge out of wood that's shaped like that. That just won't work. Or 1.5 miles or something like that, you know. That's when you would want something like these bridges. And then I told you guys to download Bridge Designer, and you're pretty much caught up to where we are today. Hooray. All right, exciting. So the Bridge Designer software is a fairly comprehensive piece of software that allows you to simulate bridges in their construction and their use. And you'll see what I mean by that when we get into it. But essentially, you can choose the materials that you're making the bridge out of. It's a little bit less than 100 megs. But pretty close to it. Whoop. But yeah, you can choose the materials that the bridge is made out of. You can choose the shape of everything on the bridge, and then you can run virtual loads across it. So you can send a truck across it. You can send, whatever, and that will allow you to test the bridge's ability to withstand weight. By that same token, we'll actually have a bridge design contest, a sort of miniature one of our own, if you're so inclined. You're not by any means required to participate in it. The 2015 version, so this top one, you want the most recent. The most recent previous version, which is sort of a strange thing to say. But yeah. Give everybody a moment to spend some time downloading this, and we'll get right into it. But anyway, yes, you are by no means required to participate in the contest. What do you mean? Because you guys are using the 2015 engineering design contest software. You're not using the 2016. Yeah, you're not using the 2016 version. So I don't understand what the issue is here. Okay, fair enough. I mean, it's still the same rules as the 2015 contest, and we're using the 2015 software. So as far as I can tell, everything seems okay. Anyway, yeah, so the least expensive bridge wins. In the event of a tie, the person who submitted earlier will win. There will be a middle school and a high school winner. Double check with Mr. Duvik about the prizes here because that was for last year, but I just want to make sure that that's still going to be the case. So take the prize with a grain of salt. Again, you're not required to submit anything, but if you'd like, you're more than welcome to. When you do it, though, go ahead and post your score on Edmodo. And you're more than welcome to submit as many designs as you like. So if you submit one and then you make another bridge that's cheaper, you're more than welcome. This slide is definitely out of date because the picture still says 2013 Bridge Designer software, but regardless, you want the 2015 version. And now that my install is done, I'm going to go ahead and run Bridge Designer 2015. Woo! Design a virtual bridge. Learn about engineering. Look at this bridge. It's got plants around it. It's got plants all around or everywhere. All the plants everywhere. Look at them plants. The Bridge Designer 2nd edition has improved support for computers with limited graphics capability. Check the help out on the Test Use Old Style Graphics menu checkbox. Yeah, okay. So give everybody a moment to go ahead and start this up. But it's pretty straightforward. When you start it up, there is going to be a dialog box that comes up that allows you to either create a new bridge design or load a sample bridge design or load an existing bridge design file. Creating a new one, pretty self-explanatory. You will be creating a new bridge design from scratch. Loading a sample bridge design will load up some of the examples that exist within the Bridge Designer software so that you can look at other designs that are successful and maybe get some inspiration. Load an existing bridge design file will allow you to load files that are examples and also ones that you've created. Excellent question. Not entirely sure. It might be because you need to enter the contest in order to use the most recent software, which is not something we're necessarily interested in. Let me double check on that though. Oh, well, the 2016 doesn't exist anyway. Oh, no, it does. Yeah, it does exist. No, you're right. Well, I think it exists now because the contest no longer exists. But in the past, it was part of that. But that's unfortunate. The Bridge Designer contest no longer exists. Anyway, regardless, whatever. Let's continue using the 2015 software. As to why we don't use it, I suppose we don't necessarily have a good reason anymore. So it wouldn't be a bad idea to explore getting familiar with the 2016 version for the next time we do this class. But for now, since we built the lesson around the 2015 version, let's continue using it. But yeah, when you use the Bridge Designer, your objective is to design a truss bridge that costs as little as possible while still passing the load test with no member failures. Essentially, that's the whole point of this. But what we're going to do is we're going to create a new bridge design from scratch. And you're going to be given this design requirement, which will look fairly similar to some of the schematics and blueprints and stuff like that that engineers will actually create in order to design a bridge. So you are given design specifications. You want to ensure that the bridge can carry its own weights, to keep the cost of the project as low as possible, and also, be able to carry the weight of a standard truck loading. You're also given a couple of views. A view of the deck that you're going to use on the bridge, which doesn't exist right now, but it will in a moment, as well as the basically a cross-section of the river that you'll be spanning the bridge across. So it has to be 44 meters long. It's going to be 24 meters up in the air, and we've got, I don't know, roughly a anywhere from 45 to 60 degree inclination on the sides. And just spitballing that. Because I am not going to do the math right now to figure out what that angle is. Anyway, you hit the next screen, enter local contest information. We're not participating in a local design contest. Local design contest is strictly for organized things. This is something that we're just sort of doing on our own. So there's no local design contest code to enter. Nothing of that sort. So in this one, are you participating in a local bridge design contest? Just keep that at no. You'll also see some more things have appeared, whereas in the previous screen we just had riverbanks and river. Now we have riverbanks and excavation, deck, and abutment and river. A few more things have been added. But we'll see exactly what those do in a moment. The third one is the big one that we're interested in. So I believe we have some standardized ones. Let me just go ahead and see this here. Yeah, here you can change the span. Oh, that's not where you change the span. I mean, you sort of change the span indirectly because you are excavating more of the side of the river in order to be able to move down further. So yeah, I guess technically that's correct. You can move it down so that it's right above the river and the span is much shorter. However, it's going to cost more to excavate. So you have to keep that in mind. You can either keep it as is. You can add an arch here in order to provide more support, but keep in mind that arches do cost more money. As you can see, it goes from 62,700 to 80,200. And if you increase the height of the arch, you also increase the cost of the project. So that's important to note. It's also kind of funky how you add more material to either side. Anyway, you can keep them standard abutments if you'd like. You can add additional supports if you'd like. So you can add a support in the middle of the bridge to be able to, lessen the load on the bridge. Now, you might be wondering, why does this not go all the way up? Well, that's because as you're designing the bridge, you're allowed to design something which connects down here using steel supports and stuff like that, so that you actually do take advantage of this extra pier here, which would provide more support. Like the arch before it does increase the cost of the project, both in adding it and also in increasing the height of the pier by a pretty significant margin. And we got cable anchorages for creating a suspension bridge. Same kind of deal, adding cable anchorages does increase the cost of the project, but not by like a whole lot. As you can see, they're only about $3,000 a piece. They are actually exactly $3,000 a piece. But yeah, as you can see, this is a pretty in-depth sort of design simulation. So even though we haven't built anything yet, just the different sort of starting designs are going to cost different amounts of money, and we can expand this over here in the lower right-hand corner with the little triangle to see exactly what's going into the cost of this. So the arch abutments, those increase the cost of the deck as well as the abutments naturally. Changing the arch, same deal. Go back to standard. Adding a pier adds a pier cost and also increases that pier cost pretty significantly. Adding anchorages will add to the anchorage cost, $3,000 per anchorage, so on and so forth. We'll keep this just plain as can be right now, just to show. Let's see. Yeah, well, that's there. But when you're working on your own project, if you decide to participate in the contest, you're more than welcome to use any of these configurations. You're not limited to one exactly. Now notice when I clicked on next and went to step 4, the deck cross section suddenly filled out with a picture of the deck. Now the deck is the thing that the road is actually on, that holds all the stuff. Like if you hold out your hand to hold an item, you can think of your arm being the support and the palm of your hand being the deck. But you've got medium strength concrete, high strength concrete. Again, you can customize exactly what you're going to make your deck out of. As you can see, it does change the thickness of the deck, which increases the weight or decreases the weight. So that's also, something important to note. So high strength concrete will be thinner, but it will also be more expensive than medium strength concrete. Medium strength concrete, on the other hand, will be heavier. And then we've got two-lane highway, or two-lane bridge and a one-way bridge. We're just going to keep with the standard two-lane. So yes, again, more stuff that you can customize on your bridge. Again, if you want to change it to high strength concrete, you can also see that it increases the cost of the deck as well. If we go back and we lower it, the deck has become cheaper. The excavation cost has gone wildly up. We go to high strength concrete, it becomes a little bit more expensive. So, it's all down to trying to figure out that optimal combination of effectiveness and cost. Again, we'll keep this all standard right now. You're not by any means required to for the contest, the Young Engineers competition thing, but we'll keep it standard right now. And then we've got templates. And these templates provide, well, blueprints for you to basically set up supports for a bridge. So you've got trusses for above and below the deck. They're called deck trusses if they're below and through trusses if they're above. We're gonna, I believe, pick the how truss. Yeah. All right, so we'll keep the how truss for now. Then you're gonna click next. There's a lot of stuff. Finally, step 6, we're just gonna put in our name. You only have 2 trusses. You mean the templates up here? I mean, in the end, it's not going to be like a huge deal. They're just guidelines, if I remember correctly. But that also could be affected if you change any of this other stuff. So like I put the cable anchorages in here, and so now I only have cable stayed Warren truss or suspended Warren truss. So that kind of thing. We'll go back to no cable anchorages and go back to the how truss. Finally here, you'd put your name. I'm just going to put Young Engineers of Today. Young Engineers of Today or YEOT. And project ID 00001A-YEOT. Now, design the deck, the span, the configuration of the abutments, whether or not there are any cable anchorages, and the truss configuration. And we've given it a name. Well, we've put in our name. As it stands right now, we've done everything we need in order to get started actually drawing the supports on the bridge. Now here's the idea. We draw the supports and stuff like that. We run the trucks across. We see what fails, and we try and fix those parts. And then you will, sit there and go like, okay, so if I actually change it this way, configure it this way, try and find the most, cost-effective way to build a bridge. And that's basically the entire point. So we'll click Finish, and here we go. Here is our diagram, our bridge, our everything right now. I've got a little floating window labeled Tools, and on this I can add joints, members, I can select them, or I can erase them. A joint is going to be a place where the struts connect to one another, obviously. A member is just another name for a strut. And by combining the two, we will build a bridge. And see, I can place them wherever. In the end, it doesn't really matter a whole lot. I can have like a bajillion joints, but let's just go ahead and undo all that stuff. Now, this is a good point. Each node costs $1,000. So each one of these joints that you add costs $1,000. For now, just, go ahead and fill in these gray squares up here. The ones on the bottom don't really need to be filled in because they technically already exist. So, don't worry about putting this one down here or anything like that. It's already there. As you can see, we've added 10, and the cost of my project is increased by $10,000. No surprise there. That's what happens when they're $1,000 a piece. The gray dots, well, you'd use the erase tool in the floating tool window, like so. The gray dots are the joints. They're what connect everything to everything else. You can add supports, or they call them members. You can add struts in between joints by just clicking and holding and drawing a line. And note that if you mouse over one of these dots, it will become highlighted, which allows you to very easily ensure that you are drawing a, uh, a, uh, a strut from one joint to another. And it will snap to it as well. As you can see, each one costs a differing amount just based on how long it's going to be, what material it's made out of, that sort of thing. Go ahead and just draw all of your struts. So exciting, I know. And with that, we've designed our first bridge. Now, the material type, as you can see over here on the member list, a whole bunch of them appeared. In fact, each time I drew one, it appeared. It's got a material type listed, a cross-section, a size, a length, slenderness, and it will update with those last two after each time we test it, which will allow us to take a look at what's failing and what is, staying okay. They're also different lengths. The diagonal ones are going to be a little bit longer, so you've got the 5.66 meter ones, and then the 4 meter ones are the orthogonal ones, because those don't have to travel as far of a distance. Size refers to the cross-section size. A cross-section refers to the cross-section shape. Material type refers to the material it's made out of. I believe it's carbon steel. And then I believe slenderness is the ratio of the length to the cross-section size. Kind of rolled my R a little bit there. Cross-section. And then see, I can click on any of these in order to highlight it in the bridge design. Now over here in the second tab, member details, this will give you details about that particular joint or strut on the bridge. No matter what I do, it says my structure is unstable. Are you running the simulation, or did you complete the whole design like I did up here? Okay. It might just be that this design is insufficient and we'll have to, spend some time fixing it, but we'll see. Something might make sense in a minute here, who knows? Okay, so yes, under member details, it gives you pretty much everything you need to know about an individual part of the bridge. Oh yeah, no, this isn't like Polybridge or anything like that, unfortunately. And it just sits there and it crunches math, and then it tells you which ones are going to fail. So it'll give you information about the material, basically how strong that material is. That's what yield stress is. Modulus of elasticity is how much it will sort of morph and stuff like that. Before, like, how much force it can take. We'll get there in a moment. Mass density is how much it weighs. Obviously, that's an important thing when you're trying to take weight into consideration on your bridge. Cross-section type will give you everything about the cross-section. It'll give you a picture of it. Here it is. So solid bar is just solid carbon steel. 140 by 140 millimeters. The area, it calculates the area, just multiplies the sides by one another in order to give you the square meters. Moment of inertia is how much it's going to take to move it. And then, of course, the member length is how long this particular bar is. Then finally, we've got the cost per meter which gives us the total cost of the member. Then we've got a graph down here of basically how the strength is affected by how long it is. So, exciting, right? Ridiculously so. Let's go ahead and let's just click this button right here. I've got it. Let me go ahead and circle it with the pen so that you can see exactly where it is. It's this sort of teal button that has a couple of arrows and a truck on it and stuff like that. That is the test button. So if we go ahead and click that, oh, there goes the bridge. Everything failed on the bridge. Super bad. Super bad, terrible. That is not an ideal bridge. You don't want that to happen. So let's take a look at this. Red is going to be, well, stress is exerted on the bridge. Blue is going to be, the opposite of that. You basically want it to have as little red as possible. The button that I showed you, it's this one up here, the teal button. Make sure you don't have, yeah, it was pretty exaggerated. Make sure you don't have any additional nodes or anything like that, and everything's connected to everything else. See, like if I get rid of this one and I try and run it, it'll say your structural model is unstable. The truss is unstable because the highlighted panel is rectangular rather than triangular. So it'll give you different examples of why. But you want to make sure that everything is connected just like how it is in the, well, at least at first, just like how it is in the design. Yeah, it could just be the particular truss I picked. Would you want to drive on this bridge? I mean, oh, there we go. So that time it was less dramatic. See, that guy doesn't want to drive on that. You kidding me? Nobody would want to drive on that. Nah. So yeah, it failed pretty terribly, but whatever. That's fine. Well, not everybody's did, but most people's did. Now, if you go back to the design part, it'll also tell you what parts failed and why. So the red is going to signify compression forces. So these failed due to compression forces, and you actually see it right here. It's being compressed, and then it fails and bends. And then these blue ones are failing due to tension. So they're being pulled too hard, and they're stretching out and becoming weaker as a result of it. So you want to keep things generally as not blue or red as you can on the whole. Yeah, that'll work as well. So now we can actually mess around with the different stuff that we have here. So let's take something that failed due to compression. And if we look at the coefficients here, the higher the number, the worse it performed. So numbers greater than 1 are failure points. As you can see over here on the tension force and strength, it just barely failed. 1.05, 1.01, 1.05, like we were hitting right at the failure point, and it was just starting to, fall apart. Really where everything had trouble was under the compression force and strength. So let's see here. You've got 1.47, which is about, 1.5 times the amount of force required to make the bar fail was exerted on that particular struts. But I want to look at this one, 1.86. 1.86, almost double the amount of force required to make the bar fail was exerted upon it. That's a lot. Nah, yeah, that's way too much force. So we've got a bunch of different nice, as in one of the compression force strength. Oh, gotcha. An expensive bridge. Oh, I see, I see. Um, very nice. But yeah, so if I select this bar, as you can see, I've got some options up here that I can mess around with. We can change the material that it's made out of, we can change the cross section of it, and we can change the size of the cross section. So right now we got 140 by 140. What happens if I put it to 150 by 150? So as you can see, it's a little bit thicker there. It's probably hard to see, but it is. And if we run the simulation, now the bars on either side of it fail, apparently. Let's try that again. Yep, the bars on either side of it fail. So you might want to do the same thing. Make these 150 by 150 and run the simulation one more time. Oh, now these bars fail out here. So it just kind of gets passed down. So it might be good to change the material of the stuff on the edges. And as you can see, the bars also change color when they're a different material. Make these 150 by 150 and 150 by 150 and 150 by 150. So we'll just change all the ones that failed to 150 by 150. Failed due to compression force, that is to say. Let's see if that evens everything out on the tension force. It might be just failing on the tension force because this stuff up here is failing, you know? You don't necessarily have to address everything in a given change. Now the bridge is still failing. All right, maybe it's time for a stronger material up here. Quenched and tempered steel. Boom. The strongest material that we have. And yep, wow, that I didn't even know bridges could do that. That's a thing. Also, hilariously, these edges are experiencing compression force and then being way stretched out. So I think the thing to be learned from this is I'm not very good at designing bridges, but it's important to note that the numbers over here are actually getting smaller, which is good. We're getting closer to our ideal strength. Whoops. So we'll go to quenched and tempered, and quenched and tempered, quenched and tempered, and quenched and tempered. And we'll make this one 180 by 180, and this one 180 by 180. Oops. 180 by 180. So we're making those bars on the edge really strong, but it's also making them heavier, which is a big problem. Man, there goes, oh, nope, bye truck. Yeah, I'm never entirely sure if I want to make them all the same, but you raise a very good point, William. You can actually box select multiple members. Okay. Let's make this one a hollow tube and this one a hollow tube. And we'll make these three hollow tubes. We'll make these three hollow tubes. And let's see how horribly this fails. Oh, the truck. Dope. So there's inconsistency in the simulation sometimes. You'll have to just go load a new design. Yeah, I'm not pretty sure that's not how metal works. It doesn't just make the bridge larger and in the ground. So clearly making those metal tubes or hollow tubes was not the best idea. We're probably going to see some failure over here on the edges. Yep, there they go. Oh, that's cool. It looks like a transformer bridge. But yeah, so this is essentially what this program is all about. If I make these 160 by 160 on either end, we can probably, dramatic. Oh, there it goes. So we'd probably be best suited making this like something like 200. Yeah, exactly. You start getting closer as you iterate through it. And everything seems stronger and stronger until you get, and then that happens again. But yeah, this is, in essence, the Bridge Designer software, and this is what it's like. Yeah, rest in pepperoni truck. Hey! Oh, there he goes. It made it almost halfway across, though. One of these days, we're going to get there. So now we just strengthen these ones, because it looks like these two are the only two that failed. Looks like that's not looking good. That one in the middle there. We made it across. All right. And then the second one, because there's a second one. Whoa. Still wouldn't want to drive across that bridge. But, if you ever wanted to build like an Indiana Jones style rope bridge for trucks, then here you go. Now let's go ahead and make this a little bit thicker as the bridge settles. Probably not. Probably not something you'd want. But yeah, so this is the Bridge Designer software. We might spend a little bit more time working on this on Monday. Yes, Monday. Otherwise, we'll figure something else out. Regardless, I'm gonna go ahead and call it for today, just because we're looking at. I'm sorry, Andrew. I'm gonna call it for today because I want to make sure we get question and answer time in before I got to get prepared for my high school class. And I want to make sure I get the poll questions out to you guys. So with that, I'll leave you with this wonderful screensaver in the background of trucks driving across my horribly shaky and uncertain bridge. Yeah, just kind of, yeah, that's what they do. They just kind of sink and then everything sort of bends and stretches. It's really weird. It's like you're making a bridge out of taffy or something. Anyway, first poll question is incoming.